Welcome students, welcome to the second and concluding lecture on the principle of inclusion-exclusion. In lecture 1, we gave a couple of examples of the instance of principle of inclusion-exclusion to 2 and 3 sets. And then we followed it up with the main theorem, the complement version and the direct version. We gave a proof of the complement version and we asked you to derive from it the proof of the direct version. Today, I will take 3 examples from the principle of inclusion-exclusion, examples of results that are otherwise very difficult to resolve combinatorially. In fact, when we apply the principle of inclusion-exclusion to these 3 cases, you will find that the formulae are a little intriguing. They're not simple single-term closed expressions. They involve alternating sums, finite sums of binomial coefficients multiplied by some other term. Suffice it to say that these results would otherwise be impossible to really work out had it not been for PIE. The 3 examples I have in mind in some order are the number of onto mappings from a set of size m to a set of size n. Sometimes I might use the word surjection. Surjection is the same as onto. And I might also use the term an n set or an m set when I actually mean any set with m elements or n elements. The second example that we will deal with will talk about the number of derangements, derangements on an n set, derangements on the set 1 to n. This is the terminology that we use for bijections, for one-to-one onto mappings from the set 1 to n to itself, in which the permutations leave no point fixed. That means they take each element I to a number other than I. More about that when I get to the example. The third and final example that I have included in today's lecture is counting the number of positive integers amongst the first n that have a GCD 1 with n. This is the well-known Euler's totient function, which we denote by the Greek symbol phi, and we will derive a formula for phi of n. Now, whereas there are other ways of deriving this formula other than the way I'm doing this. In fact, there are other ways of deriving the formula using combinatorial techniques even for the other 2. Pi remains possibly the simplest and the most straightforward way of evaluating each of these 3 functions. Let me begin with the example of determining the number of onto mappings from an m set to an n set. Before I do that, let me remind ourselves as to the formula that we used from lecture 1. This is the pi of the complementary version. Let me read this out to you to remind myself and remind us as how we are going to apply it. So let me read along. X is a finite set. A1 to An are non-empty sets of X. The number of elements in none of the sets Ai is given by the sum on the right. In the sum of the right, the term A sub I stands for the intersection of the Ais, and with a special notation for A sub phi, and that is X. Now, in each of the 3 problems, the difficult part initially is to figure out what to choose for the set X and then what to choose for the sets A1 through An. But the problem is not over once you've resolved that, because then we have to carefully evaluate A sub capital I for each I subset of n. and only then will we be able to figure the three problems out. Let me begin by talking about the number of surjections, number of onto mappings, from an M set to an N set. We're used to looking at this in terms of two pictures, two Venn diagrams to denote these sets. We can call the set A and call the set B. And we can put some dots in here to denote the elements of A. This is an M set, so there are M elements in here. And the dots in B are these. This is an N set, so the number N is put out there. I could simply take the instance when A is in fact the set 1 through M, denoted by the square bracket M, and B is a set 1 through N, denoted by the square bracket M. Now, we want to find the number of onto mappings from an M set to an N set. We have to apply the formula for pi in the indirect version, in the complement version. So we must first and foremost decide what is X and what are the sets AI. Well, maybe I can write it right here. For X, I use the set of all functions. I've used the terminology mappings and functions interchangeably. Set of all functions from the set A to the set B. I've taken A to be the specific set 1 through M and B to be the set 1 through N. So this is X. This is fairly obvious because I want to pick a set which is larger than the set that I want to evaluate, and at the same time is a set whose size I can measure. It's quite easy for me to figure out the size of the set X. What is the size of the set X? So notice the size of the set X is the number of functions that start from A and end at B. So for each element in A, I have n choices, and therefore the total number of functions is n to the power of m. In fact, you might notice that this is exactly equal to the cardinality of B to the power the cardinality of A. And so it might not surprise you to note that in combinatorics, the set of all these functions here from A to B is called simply B to the power A. So when we write B to the power of A, it is a notation that stands for the set of all functions that go from this power to this base. And we use that notation because it quickly reminds us that the size of that set of all functions, is simply the size of B to the power size of A. Now, we need to find out what the sets AIs are. Let me write down A1 and so on to AN. Let me think for a bit as to what I want to do before I decide on how to choose these sets. The complement version of pi counts the number of elements which are not in any of the sets A1 through AN. So I want to pick for A1, for instance, all those functions that I do not want to finally count. The functions I want to count are functions that are onto mappings. That means they are functions that have a range equal to all of B, all of the numbers from 1 to n. So I want A1 to be some set of functions that do not include any of these functions that are onto. So this decides for me a natural choice for such functions. So these are all functions from A to B such that the range of f, which I'll call RAN for short, the points where f goes to, this does not include, does not contain, so maybe I can write this out like this, does not contain the number 1. Let's pause for a minute to figure out what this will eventually give us. Obviously, once I say that A1 is all those functions so that 1 doesn't belong to the range, I'm going to write at the end of it, for fn, for instance, the fag end of it, the last bit, all those functions, so that n does not belong to the range of f. I could have written this a little more compactly as 1 does not belong to the range of f. But before we go ahead and try to count these sets and other related sets, let's make sure that my left-hand side of pi, which counts x minus the union of ai's, actually does what I required it to do. This is the left-hand side of pi. So the left-hand side of pi counts all the elements in x, but in none of the sets ai. Now, all the elements of x are, of course, all possible functions from a to b. We want to throw out those that are not onto. But what does a1 do? a1 counts all those functions that are not onto because 1 is missing from its range. a2 is all those functions that are not onto because 2 is missing from its range. a3 are all those functions that are not onto because 3 is missing from its range, and so on and so forth. And now if something is not onto, it's clear that one of the numbers, at least between 1 and n, will be missing from the range of the function. And therefore, it must be included in the union of the ai's. Therefore, the left-hand side, in fact, counts the number of onto functions from A to B. This is a very important first step, because if you do not have your set X and or your sets A1 through AN correctly written up, then applying pi is not going to help you, because you're going to be counting something different from what you're asked to count. So this is a good place for you to pause and think about what I just said. Make sure that the choice of X and the choice of A1 through AN actually gives you, from the left-hand side of pi, the number we seek, the number of onto functions. Having figured that out, we simply have to now evaluate, which is a second part of pi. We have to evaluate by using pi what we get for the formula for the number of such mappings. What is the right-hand side? The right-hand side is a sum over the indexing set I, sum over all subsets of n, minus 1 to the power number of elements in I, multiplied by the number of elements in ai, where, and since we're not very familiar with this, I will need to write this down a few times, ai is in fact the set consisting of intersections of ai's where I belongs to I. This is what we need to evaluate. So instead of jumping straight for the general I, let's do this in steps. Corresponding to I equal to the empty set, and we did this in the first lecture, we get the singleton set X. And then there is a bunch of sets that we need to intersect one at a time. This is simply the cardinality of the AIs, followed by plus cardinality of the sets that look like AI intersection AJs, and then a minus 3 at a time, and I put dot, 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 and plus 4 at a time, and I put dot, dot, dot. And all we have to do, therefore, is to evaluate each one of these. Well, let's look at the first few, and then perhaps we'll be able to figure out what the general pattern is. So let me keep this formula for pi that I wrote down just now so that I can refer to it. Let's look at the number of elements in X. The number of elements in X is the set of all functions from A to B, and we know this to be n to the power of m. The second term involves terms that look like the cardinality of the number of elements in A1. Let me draw a little picture to illustrate this. Here is A has m elements. Here is B has n elements. So I put the elements of A as dots out here. I have 1 in B, which is the first element, and then there are n minus 1 other elements. Now, I'm looking at functions that go from A to B, but 1 is not in the range. So let me factor this out. And let me look at all those functions f that go from A to B minus a single element. Now, each of these m elements therefore have n minus 1 choices, and therefore the total number of such functions is n minus 1 to the power of m. As a matter of fact, it doesn't matter which element I've removed. I could argue that for each AI, the number of elements is n minus 1 to the power of m. And therefore, the contribution to the sum AI, taken one at a time, is simply the total number of such sets multiplied by n minus 1 to the power of m. And the total number of such sets is n choose 1, or n, because there are n sets A1 to AN. Let me do one more of these before I try to write a general formula down. What can I say about the cardinality of A1 intersection A2? In A1 intersection A2, if I use the same picture as before, my domain of the function is of course the same. My range is in fact restricted to within the subset n minus the first two elements. Therefore, the cardinality of this is n minus 2 to the power of m, because the first two elements are not in the range. And I can consider any function with codomain which includes the numbers from 3 to n. Again, as before, if I were to look at AI intersection AJ, regardless of whether it's 1 and 2 or any A and J, the answer is the same. It is irrespective of which two elements I've removed. And therefore, AI intersection AJ is n minus 1 to the power of n minus 2 to the power of m. What is therefore the contribution to the sum of AI intersection AJ? Make sure this comes under this thing here. This is n minus 2 to the power of m multiplied by the number of ways in which I can choose these two sets AI and AJ distinct from the n sets, and that is simply n choose 2. Get a fresh sheet. I still have this general formula written there. I therefore get the number of onto mappings from an M set A to an N set B is, and I write the cardinality of X first. What we had was n to the power of m. Then the sum total for the first term sigma AIs, which was n choose 1, and then n minus 1 to the m. For the second one, it was n choose 2, the number of ways in which I could choose the symbols I and j from two at a time from the first n numbers, n minus 2 to the power of m, and so on and so forth. All of which we could write more briefly as a summation, single summation. I goes from 0 to n, minus 1 to the power of I, n choose I, n minus I to the power of m. This then gives you the formula for the number of onto mappings from an M set to an N set. Some of you would have recognized that if M is equal to N and this mapping is onto, then this mapping is also 1 to 1. On the other hand, if you have a 1 to 1 onto mapping from an N set to an N set, the sizes have to match, then any such mapping is called a bijection. It's called a permutation of those numbers if the sets are equal. And we know that formula to be n factorial. So although this may be hard to otherwise derive, if you put m is equal to n in this, we must get n factorial. So this is an identity which would otherwise not be so easy to derive. N factorial is sigma I from 1 to n minus 1 to the I, n choose I, n minus I to the power of n. It's time to go to my next example. The next example I've chosen for you is the example of derangements. The concept of derangements may be somewhat alien to you. Let me first explain what a derangement is. The standard way of giving an example of a derangement is to think of letters and envelopes. An equal number of letters and envelopes. Let's say you have n letters and n envelopes. And you are in a situation where you're writing letters, you're applying for a job to 10 different people. You are doing things in a hurry. You're not being careful. You address a letter to Mr. X, but in the envelope heading, it goes to Mr. Y. A situation could arise, and this is rare, where you actually end up putting the wrong letter in each of the n envelopes. You would imagine that if n is large, this is a situation which will rarely occur. For example, if you take n equal to 10, you're applying to 10 different jobs, and you have 10 addresses written on these 10 envelopes, and you have 10 letters typed out, and you're trying to figure out, or you're hoping that this doesn't work, how many ways can I totally mess up? You totally mess up when none of the letters are addressed are put in the right envelope. Well, take a guess as to how bad things can get for each n. Well, here's a little table I have of derangements. The symbol we use for derangements of an n set is just dn. So dn counts the number of derangements of an n set. We could assume that n set to be 1 to n. And we're looking at the permutations of 1 to n, in which pi, which is a permutation of the set n, has the property that pi on any symbol I is not equal to I. And this is true for every I in the set 1 to n. So for example, if I just take the instance of n is equal to 3, and I have a permutation, what I'm required to do is to rearrange the numbers 1, 2, and 3 in some order, such that what I fill under 1 is not 1. It could be 2 or 3. Let's say I put 2 here, then I'm left to put 1 and 3 in the other 2 slots. Since I can't put 3 under 3, 3 must go under 2, and therefore 1 comes here. Now I chose to put 2 under 1. I could have put 3 under 1. Then I'm left with 1 and 2 to fill. I can't put 2 here, so I must put 1 here, and that leaves me with 2 there. There is no other possibility to put under 1, because I can't put 1 under 1. So in this particular instance, I have an illustration that D3 is equal to 2. This will take me a little bit astray, but in fact, we can prove, and this is not what we're going to do today, a formula, a recurrence formula for dn. It goes dn is equal to n minus 1 into dn minus 1 plus dn minus 2. This is an example of a second order recurrence. It basically means to evaluate dn, I need to know each of the 2 immediately preceding terms in the sequence. So I must know to evaluate this, to evaluate 3, for instance, 1 and 2. In fact, if I know the first 2 terms of the sequence, I have completely determined the sequence. But we don't know this. This is a fact that I'm pulling out, and I will place before you a table of derangements. I don't have space to write more, because you can see that this table occupies a lot of space very quickly, the numbers increase fairly quickly. It's easy to see that d1 is 0 because 1 must go to itself and there's no other possibility. d2 is 1 because the only possibility to mess up is to send 1 to 2 and 2 back to 1. d3 is 2 as we just figured out. And to figure out d4, you multiply by 3 the sum of the immediately 2 preceding numbers. So 2 plus 1 is 3, multiply by 3 you get 9. To get the next one, you have to multiply by 4. Under 5, you have to multiply by 4, 9 plus 2, and so on and so forth. This is how you complete the table. But this is not about completing this table by a formula that we haven't derived. This is more about actually applying pi to evaluate a formula that we're going to derive quickly. So as before, and I'm going to run through this a little faster, we have to take a universal set. There's an obvious choice for a universal set. After all, a derangement is a permutation. And therefore, we take X to be the set of all permutations. And we know this number to be n factorial. So far, so good. What I need now is to decide what is A1 and so on and so forth, all the way up till AN or AM or whatever the symbol is that I choose to have. So what would I like my A1 to be? Well, you have to back calculate in all these problems that involve the complement of pi. At the end of the day, the left-hand side of pi is going to give me the number of elements in none of the sets A1 to AN. What do I want that to be? I want that to be a derangement. And therefore, if I take the opposite of that, a derangement is something that messes up each of the symbols. The opposite of that will be things that don't mess up each of these symbols or one symbol at a time. And therefore, A1 will be the set of all those permutations pi, which keeps one fixed. So pi is a permutation, and A1 is all those permutations that send 1 to itself. We don't worry about what it does to 2 or 3 or 4 and so on. Therefore, in a similar fashion, I will define AN to be the set of all those permutations that take n to itself, with an obvious definition for each I. So AI will now be the set of all those permutations that sends I to itself. Before we jump into the problem of counting what these sets are, what the size is, and so on and so forth, let's make sure that we are, in fact, going to be counting dn from the left-hand side of pi. So what is the left-hand side of pi? The left-hand side of pi is going to include exactly those elements in X, permutations, that are in none of the sets A1 to AN. Now, what does it mean to say it's not in A1? If it's not in A1, it does not send 1 to itself, because A1 is all those elements that send 1 to itself. In a similar manner, if it is not in A2, it does not send 2 to itself. And if it's not in AN, it doesn't send n to itself. Therefore, if it's in none of the sets A1 to AN, it has the property that it sends nothing to itself. Now, that's exactly what dn is. dn counts those permutations which have the property that pi of I is not I for each I. And by hitting upon the choice of sets A1 to AN and X, the way I have, we are in business. All we've got to do now is to evaluate the right-hand side of pi, and if we do it correctly, we should be able to evaluate dn. We should be able to find a formula for dn. So let's begin at the beginning. Let's look at, to begin with, the size of A1. This is all those permutations which leave 1 fixed. Well, let's take one out of the equation, one of the picture. What does this permutation pi do? It kind of permutes the other n symbols. It sends the other n symbols to the remaining n symbols in whatever way, including fixing 2 or fixing 3 or whatever. So this is simply the number of permutations on n minus 1 symbols, and that's just n minus 1 factorial. In fact, the same is good for any of these sets AI including an, because each of these sets ai fix one particular element. They leave the other n minus 1 elements to themselves, which may and may not get fixed, and therefore it is a set of all permutations on all but one symbol. The contribution therefore to the sigma ai is, as before, the number of ways of choosing these single sets, one element I from n choose one ways, multiplied by n minus 1 factorial. Now let's look at what happens when I take the sets two at a time. For example, A1 intersection A2. A typical element in A1 intersection A2 is a permutation. It is common to A1 and A2. Therefore, it takes 1 to itself and it takes 2 to itself. So whatever I do, I know what the answer is to pi of 1 and pi of 2. I only have to figure out what the possibilities are for the other n minus 2 symbols. And these n minus 2 symbols can be chosen in any which way as long as they are a permutation. Therefore, the number of elements in A1 intersection A2 is just n minus 2 factorial. This in fact is true for any two sets ai and aj, I not equal to j, because 2 points are fixed, the other are freely chosen, can do it in n minus 2 factorial ways. And now the contribution to sigma ai intersection aj, as before, is n minus 2 factorial for each of these terms multiplied by the number of ways in which I can choose these terms. I can choose two elements from n elements in n choose two ways, and therefore I end up with n choose 2 multiplied by n minus 2 factorial. Therefore, from pi, from the right hand side of pi, I get sigma minus 1 to the power of cardinality of I subset of n, into the cardinality of a number of elements in ai. And now if I further classify this in terms of the number of elements in I, in other words, let I stand for the number of elements in I, then I could go from 0 to n. The first term is minus 1 to the power of I, because I've chosen all those i's, I've categorized them, I've clubbed them together, all those i's that have exactly I elements. And what is the contribution to ai? Well, for a specific ai, the contribution is simply n minus I factorial. To get the whole contribution, I have to multiply this by n choose I. That's the total number of ways in which I can choose a specific I subset of square bracket n. For each such I, the number of ways of finding out the number of elements in ai is n minus I factorial. And therefore, this is the formula that you get for d of n. We can simplify this a little bit. If you simplify this a little bit, you get I from 0 to n minus 1 to the power of I. And I could write this as n factorial over I factorial n minus I factorial. And I multiply by n minus I factorial. And I can cancel these two terms out here. And I could write this as n factorial, which is independent of the index of summation, minus 1 to the power of I over I factorial. This then is the formula for dn. It cannot really be simplified. You're adding alternately plus and minus the reciprocal of factorials. Let me put this in a different slide. To summarize, dn is the sum I from 0 to n minus 1 to the I, n choose I, n minus I factorial. After a very simple simplification, you get n factorial into I from 0 to n minus 1 to the power of I by I factorial. The thing that I wrote in the end comes from the following fact, and it kind of answers the question that I asked. dn over n factorial is simply sigma I from 0 to n minus 1 to the power of I over I factorial. You would recognize this to tend to e to the power of minus 1 you will recognize the expansion of e to the power of x, which is sigma x to the power of n by n factorial, n from 0 to infinity, or I from 0 to infinity, x to the power of I by I factorial. And now if you take the limit as n tends to infinity in this is just 1 by e. So this is what it tends to as n goes to infinity. So to answer the first question, although this is not valid for something as small as n is equal to 10, as a proportion or as a fraction of all permutations, the number of derangements in the limit when n is large, which is given by the limit as n goes to infinity of dn by n factorial, it is actually 1 over e. And some of you may remember that e is about 2.7. It's certainly less than 3. And therefore, as a proportion when n is large, the number of times that you can totally mess up when you have derangements is somewhat bigger than a third. It is something like 1 by 2.7. And to think that when n is large you can mess up more than a third of the times is something that is not intuitively obvious until it is shown to you by this formula. I'm going to close with a third problem which has its roots in number theory and algebra. Let us take the set of positive integers up till n, and let us talk about the set S of all those integers a between 1 and n, which have the property that the GCD of a and n is 1. Let me call this S sub n, although S sub n is not a great notation because S sub n typically stands for something else commonly in mathematics. But still, for the sake of today's lecture, let me just call this S of n. As an example, what could I say is S of 12? S of 12 would count the numbers between 1 and 12, whose GCD with 12 is 1. 1 would qualify, 2, 3, and 4 would not, 5 would qualify, 6 would not, 7 qualifies, 8, 9, 10 do not, and 11 qualifies, and 12 does not. So S12 consists of these 4 numbers. I'm more interested in figuring out the size of that set. More generally, if I look at this Sn, the number of elements in such a set is what we call phi. This phi is called Euler's totient function. Or sometimes called Euler's phi function. That is the Greek letter that symbolizes it. I have a little table to compute phi up to 10. Unlike dn, this is not a function that grows very rapidly. In fact, it doesn't even grow. It is not an increasing or a decreasing function. The behavior of phi n is kind of random. It climbs, then comes down, and then climbs, and you don't really know what's happening here. Actually, phi n is related to the way that n factorizes into prime numbers. So here's a quick table of phi n for n between 1 and 10. You can store it, and you can check that this table is accurate by listing the elements in each of these Sn's. So for example, if you look at the last one, S10, the numbers that go into that set are the numbers that share nothing in common except 1 with 10. So because 10 has 2 and 5 in it, we must exclude the even numbers, and we must also exclude 5. So therefore, we are looking at the odd numbers other than 5. These are 1, 3, 7, and 9. Therefore, phi of 10 is equal to 4. We're going to apply pi, the principle of inclusion exclusion, to derive a formula for phi n. Again, in this example as well, x kind of defines itself. For x, I will take the set n, the set of all the numbers up to n. Now, because it depends on n, naturally I have to list the primes p1, p2, p3 till say pk. Let these be the primes, the prime divisors, prime factors, prime divisors of n. The number of prime divisors of n is something that one can't really figure out, and therefore I cannot predict for you how many of these primes I'm going to write down. If n is greater than 1, if n is not 1, that list will include at least one prime. At any rate, I've written down the list of all prime divisors of n. So for example, if n is 12, that list will include only 2 and 3. And if it is 10, it will include only 2 and 5. Now let me write down the sets. Let me begin with A1, which has naturally something to do with the number, the prime number P1. So what do I really want here? First and foremost, I want all those numbers, call it m, between 1 and n. I never go outside that set, which has to have a property that makes it not count towards 2 phi of n. Now what is phi of n? Phi of n includes all those numbers that are co-prime to n. That means they don't share any divisor with n, any divisor greater than 1. And because numbers are built up of building blocks, atoms called primes, we really have to focus on the prime numbers. If I can therefore say that m is a multiple of P1, for instance, then m will have P1 in common with n. If it has something in common with n, then that is what I want to put in A1, because ultimately I want to count all those numbers that are not in any of the AIs. So in some sense, the AIs have to be numbers that have something in common with n. So the first thing I do is I look at all these numbers m between 1 and n, so that P1 divides, and that vertical line there is the mathematical symbol that says divides, it divides m. So the symbol here is divides. That's what A1 is. What is A2? Well, the same thing with P1 replaced by P2. And what is AK? AK are all those numbers, so that PK divides m. So now I have a situation where all the sets are defined, A1 to AK. I don't go till n because I've used n for a different purpose, and I may not assume that there are exactly n prime divisors of n. So therefore, I'm going to use a different subscript to denote the number of sets, k in this case. Let me take a minute to again reconfirm that what I'm looking at from the left hand side is what I want. What is not in any of the AIs? Well, they have to be in x, so it's certainly an integer between 1 and n. If it is not in A1, then P1 is not dividing that number. If it is not in A2, then P2 isn't dividing it. If it's not in AK, then PK isn't dividing it. Therefore, if it is in the complement of the union of the AIs, that number is divisible by none of the numbers P1 to PK. But there's no other prime that divides n. Because there is no other prime that divides n, therefore this number must be co-prime to n. Think about it. If there's a GCD, if there's a common divisor between m and n, and that common divisor is more than 1, there has to be a prime number that divides both of them. Because every number is a product of prime numbers. And that prime number is not from P1 to PK, because m is in none of these sets, and therefore doesn't exist at all, because there is no other prime that divides n. So therefore, we have the right x and the right AIs. Let's look at what A1 is. Well, A1 is the multiples of P1. It's rather straightforward to figure out what the size of the set is. How many multiples of P1 are there up to n? Well, obviously n by P1. For example, if n was 10 and p1 was 2, how many multiples of 2 are there up till 10? Well, positive integer multiples, well, there's 2 and there's 4 and there's 6 and so on, all the way till 10. So it's 1 times 2, 2 times 2, all the way till n by 2 times 2, 10 by 2 times 2. So in short, the number of multiples of p1 up to n will be n by p1 times p1 up to there, and therefore it will be n by p1 multiples of p1, and therefore the size of the set A1 will be n by p1. In much the same manner, the number of elements in AK will be n over pk. Notice an intrinsic difference in this problem from the other two, which is why I'm doing this later. In each of the previous two problems, the size of the sets AI were the same. In fact, the size of the sets AI intersection AJ were the same. So it didn't matter whether you were counting A1 or A2 or A3 or AK or AN. They all had the same size. Because they had the same uniform size, the binomial coefficient came in. The number of ways of choosing a set of a certain size came in. The binomial coefficient n choose I came in. It was typically the size of A sub I was over all such i's, n choose I multiplied by whatever was specific to this problem. Not anymore, not for this problem. Because in this problem, the size of A1 and the size of A2 and the size of A3, etc., do not match. Okay? So on one hand, one has to be careful about writing down the right formula for each of these. On the other, one doesn't have to worry about how many ways I could have selected the sets. What happens to A1 intersection A2? Well, A1 intersection A2 consists of all those numbers m from 1 to n, which are in A1 and in A2. If it is in A1, P1 divides it. If it's in A2, P2 divides it. So m is a common multiple of P1 and P2. Therefore, it's a multiple of the least common multiple of P1 and P2. But P1 and P2 are primes. The LCM of P1 and P2 is P1, P2. And so in fact, the numbers that go into the set A1 intersection A2 are multiples of P1, P2. So therefore, this number is n over P1, P2. And more generally, if I were to write AI intersection AJ, the size of that would be n over Pi, Pj. Now, you can take this by continuity, that if I were to try to do this over 3 sets, let me write this one extra one down, A1 intersection A2 intersection A3. I'm really looking at multiples of P1, P2, P3, and there would be n by P1, P2, P3 of them. And I could generalize over any 3 sets. AI intersection AJ intersect, I should have used K because that's what comes later, but I should not. Let me invent a symbol called L. And this would be n by Pi, Pj, Pl, because I've used up K for a specific set as the last of those sets. From pi, this is always the complement version, I get phi of n is, and let me write down the first few steps, the number of elements in X minus the number of elements in a typical AI plus the number of elements in a typical AI intersection AJ, and so on and so forth. How many elements in X? Well, I know that, n. How many elements in the AIs? Now, it's not an n choose I sort of a thing or n choose 1, because different AIs have different number of elements. So you might recall A1 had n by P1 elements, A2 had n by P2 elements, and AK, and so on and so forth, AK had n by PK elements. Not so nice, because the terms are all different. I need to worry about this. What about the AI intersection AJ? Well, I begin with A1 intersection A2. I know this to be n by P1, P2, and then so on and so forth. And I kind of end with n by Pk minus 1 Pk. All the numbers taken 2 at a time, the primes, they form the denominator. And the whole thing is n divided by that. and then I have minus dot 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 plus dot dot dot. And what do you think the last term would be? The last term would correspond to taking the sets all at a time. So my last term would be minus 1 to the power of k over n by p1, p2, dot dot dot, pk. Now, can I simplify this? The first thing that strikes me is I can pull this n out, and I get 1 minus, and I have something like sigma 1 by pi plus sigma 1 by pi pj, and then minus sigma 1 by pi pj pr, pl, whatever, dot dot dot, plus dot dot dot. I can write the last term, doesn't help a whole lot, but it's a single term, there's no summation there, minus 1 to the power of k over p1, p2 till pk. I probably just about have space to sneak this in. So this is equal to n, and check this out. This is 1 minus 1 over p1, 1 minus 1 over p2, dot dot dot, 1 minus 1 over pk. How do you get this? Well, look at a typical term out here. What is the constant term? The constant term is 1. What is the term which has ones chosen from every box except one of them? So that's like getting minus 1 by p1, getting minus 1 by p2, and so on. And that accounts for the first term in the summation out here. What happens if I take them two at a time? If I take them two at a time, I have a typical term that looks like 1 by p1, p2. That comes with a plus sign. And so on and so forth. So if you actually multiply this out, you will get what I wrote there. This then is a formula for phi n. I could write this more briefly as n, product, 1 minus 1 over p, p divides n. What happens when n is 1? Because when n is 1, there's no prime that divides it. When there's no prime that divides it, the product that I'm writing is an empty product. It's a product over an empty set. How do I define that? Well, I typically define that to be 1 by convention, or I simply write a separate formula for phi 1, that is 1. Well, I hope you enjoyed each of the three mathematical problems. Two of them used pi in a certain way. The third used it in a slightly different way. Suffice it to say that these problems could not have been solved directly by other techniques other than pi quite so easily. There are other combinatorial techniques or number theoretic techniques would actually resolve the second and the third problem, the one on derangements and phi. But it is probably commonly believed and understood that pi is the correct way to solving these problems. I would encourage you to look at more problems on pi from textbooks, from internet, from other sources, or by asking your teacher. Thank you.